Okay, so here we are with 8.3. We went through all of the population proportions. Right now, we're going to estimate a population mean. So we're actually going to gain two more formulas. The first one I'm going to show you, I'm going to talk about it for a little bit, and then probably might be the last time we talk about it because it's actually very rare to use. But if you were doing a, say, one sample z interval for means, right? Typically, we don't use a z interval for means because when you see the formula, it actually kind of contradicts the whole idea of creating the interval, right? But it does happen, from time to time. So we would take the same format, right? So if you think of the same format, we had this doesn't change. We had our point estimate plus or minus the margin of error, right? And the margin of error is your critical value times your standard error. Okay, so the point estimate for a population mean, the point estimate would be x bar, right? Because we're estimating mu. So instead of having mu, we're going to use x bar to estimate it, right? And then we're going to have, obviously, we're going to use the z as the critical value, so that'd be a z star, and then the standard error we know from before, and this is why I kind of use this to intro this because we're familiar with the standard error of sigma over the square root of n. So with that being said, you think about this, in order to have sigma, right, this is kind of just a side note, and if you had to know sigma, that would be the square root, and you had to do the sum of all of the x sub I minus mu squared over n, right? Well, in order to find sigma, you need mu. And the whole purpose of an interval is because we don't know mu. So this kind of contradicts itself in its own, thing. So if we don't have mu, we've got to estimate sigma, and then we have to use s. Okay, so with that, kind of introduces a whole new thing. And I'm going to kind of start this. This will be a one sample. This is where the t distribution comes in. This would be a one sample t interval. Okay, so the only time you're ever going to use this one is if you happen to know sigma. And chances are you're not going to know it. It's going to be coming from the sample, so you have to use S to estimate it, which means we have to change Z, right? So, why do we have to change Z, right? So, good question. Let's take a look at our thing here, right? So I got a little applet for you, and what we're going to do, right, I just have some values in here. Say the true mu was 100, right? Again, this is usually unknown. Sigma, say, was 20, right? Again, if we don't know mu, then we're not going to be able to know sigma. And let's just say we're taking samples of size 4, for example, right? It's coming from a normal distribution. And then let's just say we use a z with the s and see what happens, right? Confidence level is 95%, right? So we sample and we start going through, and all right, so let's just speed this up. Let's just say let's reset this, and let's say we take 100 samples. Okay, here's 100 samples using z with s as the estimate. So s is the sample standard deviation depending on, here's your 4 values. Whatever that s is, that's what we're using to estimate sigma, right? And, an s is an unbiased estimator of sigma, but with the sample size being so small, sometimes that's a little bit further off than we really want it to be, right? Because remember, the overall goal is we want a 95% capture rate. Well, if I look at out of 100 of these intervals, I'm only at an 87% capture rate, right? So if I continue to do this, right? I'm not getting my 95% capture rate like I need to, right? So I've got to fix that, because if I say it's a 95% interval, I want it to be a 95% interval. I want it to capture about 95% of the time, not 80% of the time, or 85 or 86% of the time. I want it to be 95. So what we're going to have to do is, if we're using S, right, the sample standard deviation coming from the data here, if we're going to use that, especially for smaller sample sizes, we've got to find a way to, or think of a way to increase our interval, right? So we think, well, we can't change the sample size, right? That's going to stay the same. But how can we increase the interval, with keeping this, say this was 4. I want to do samples of size 4. How do I get that 95% rate? Well, what I'm going to do is I need to, again, like I said, I increase the width of the interval. So I don't want to change the confidence level. So what happens is, instead of using a Z, that's where we introduce what we call a T distribution. Okay, so a T distribution, if you look, the same thing, right? So let's reset this and do the same thing, same numbers, same number of intervals, right? And we start sampling, and what you're going to notice, right, is now you look at the running total, we've got that 95% capture rate. So that's what we want. We want that 95% capture rate, so we have to use S to estimate sigma. So that means we're going to have to replace Z. That's where I said everything's got a trade-off. If you don't have sigma, you use S. Well, if we have to use S, then we can't use a Z, and we've got to find a different way to keep that capture rate, because that's what we're saying this is. We're saying it's 95%, so we want to keep it at 95%. So we have to change the Z to a T, right? And they are related. The Z's and T's are related, right? So when you look at this, the T distribution is actually a kind of umbrella or a family of normal distributions. It is a normal distribution, and they are a family of normal distributions, and the Z turns out to be a special case of the T. Quick story here. This is where the T distribution actually came from. There was a guy, his name was Gauss, and he, or I'm sorry, not Gauss, Gosset. Um, he worked. He was he worked for Guinness Brewing, and he was trying to make better product for the consumers. And he was using, they had statistics, and they were using all this stuff, and he wanted to make better product, and he started using estimating with this new T distribution that he kind of figured out. And back in the day, I mean, you're talking 1800s kind of thing. He couldn't publish anything, because if he would have gotten in trouble for publishing his work, he didn't want to secret out or whatever that he worked for Guinness, and then everyone's stealing his ideas and this and that. So what he did was, he actually published it under this whole distribution, this whole idea. He published it under the pseudonym of Student T, and to this day we call it a T distribution, because it came from the Student T. Sometimes we'll even see it as a Student T distribution. So that's actually kind of pretty cool that it's still, that's why how it came up with Student T is because he just called it himself Student T, and created this kind of saw this distribution and how it worked, right? So with this, right, if I go into my calculator, just kind of show you what a T distribution is, I've got a bunch of T distributions here, right? So this is actually kind of a cool way to see how this is the only time I ever told you to ever use a PDF is if you're going to graph them, right? So let me turn these on, and your T distribution is actually dependent on a degrees of freedom, right? That's what this number is here. It's called a degrees of freedom. The normal distribution doesn't have a degrees of freedom. Now let me turn off this plot one. Right, so your T distribution all depends on degrees of freedom. So what you're going to see is, and actually if I take this off, let's take this one off and this one off, right? So T distribution, where it has a 2 degrees of freedom, right? Which would actually mean it's a sample size of 3, right? So let's change our window. Let's make this, let's go from negative 3.49, right, to 3.49. That's kind of like our standard, and then for y, let's just make this like negative 0.01, just so we can see some stuff. And then we only really need to go up to say like 0.4, all right? And you graph this, right? And that's the t-distribution with a degrees of freedom of 2, okay? It looks pretty normal, right? So let's go back and actually let's change this, turn the rest of these on, and what you're going to see is as the degrees of freedom goes up, and then this last one, so the pink one you're going to see is the actual normal PDF or the normal distribution that we've seen, previously, right? So with that, right, there's 5 degrees of freedom, there's 9 degrees of freedom, and there's your normal distribution, right? So really, what you're seeing, those of you who took calculus and looking at limits as n approaches infinity kind of thing, this is where it's kind of cool to see the connection between calculus and stat, which there is with the t-distribution. So the pink one's the one we've been dealing with. That's the normal distribution. You notice this was let's get back. I forget what it. So 2, 5, and 9, right? So blue, this is 2 degrees of freedom, 5 degrees of freedom, 9 degrees of freedom. There's your normal, right? So what you're seeing is as this, right, if you can see my pointer, the blue one to the red one to the green one to the pink one, it's going from smallest degrees of freedom of 2 all the way to your normal. So basically, as n starts to get larger and larger and larger, it starts to converge onto the normal distribution, right? So I'm going to add actually one more in here. And let's make this one, right? We've talked about the whole n greater than 30, or at least 30. So let's make this, let's say 29 degrees of freedom, right? Because then, and if we graph that, let's change the color so it's not in the same color. Let's make that one orange, that's fine. Okay, and graph it. And you're going to notice, see how the orange one's almost on top of the pink one, right? There's where the whole n is at least 30 thing came from, because your t-distribution basically turns into the z, once you get to that sample size of at least 30. All right, so that's where the t comes from. It's very complicated to come up with the whole distribution. It's like the one thing that when Gossett did this, I think I'm saying his name right, Gossett. If not, I apologize to Mr. Gossett. But that's where the t distribution's coming from, and that's why when we do this, we need to use the t when we use the s, because it helps keep that 95% capture rate. All right, so there's the I guess the beginning of 8.3, right? So stay tuned for part 2, where we actually get into some of the t intervals and the formulas and things like that.